Hi, this is Mrs. Blake, and today we're going to start talking about electron configurations. This is the first of a multiple part video series to help you understand the idea of an electron configuration and quantum numbers. In order to take a look at electron configurations, what are we really taking a look at? We look at how do we define where electrons are located. So let's start with a little bit of review and figure out what we know about electrons already. Well, we know that electrons are located outside the nucleus. But usually, when we talk about atomic structure, we leave it at that and know that protons and neutrons are in the nucleus, but electrons are on the outside. We know that electrons have a very small mass, and so small that it's insignificant when we're trying to count the mass of an atom because it's just that small. And then, probably one of the more important things that we need to remember is that electrons have a negative charge. That's going to play an important role in where electrons are located, because with that negative charge, we know that the nucleus is positive and that there is an attraction between the two of them. So, throughout history, as we're taking a look to figure out what electrons look like, there were several people who worked on this problem. And one of the guys that worked on this problem is a guy named Niels Bohr. Niels Bohr developed the Bohr model of the atom, which is one of the most recognizable symbols in chemistry. In Niels Bohr's experiments, he experimented with energy in atoms and realized that atoms, or more specifically electrons, emitted light. From his findings, what Niels Bohr realized is that there were really two states for an electron, and these are both terms that you probably want to have written down because you will probably see these again at some point. The first term is a ground state electron, and a ground state electron just refers to an electron at its lowest energy level. And the second term is an excited state. So if I add energy to a ground state electron, it gets excited and it moves up energy levels, it has more energy, and we call that an excited state electron. So excited state electrons are electrons which added with energy added that change their energy levels. Bohr's biggest contribution to the arrangement of the electrons comes in those energy levels. Now, if you look at a traditional Bohr model, you are going to see rings or circles where electrons are located, and those are the energy levels. So we'll refer to this as n equals 1 as the first energy level, and the second energy level, and the third energy level, and so on as you go out from the nucleus. Know that as you go from the nucleus, the lowest energy levels are near the nucleus, and the further out you get, the more energy that you get. Well, when we take a look at energy levels, then, energy levels correspond to the periodic table. So when you see the rows on the periodic table, the rows are going to be the energy levels of those electrons. And if you look at the first two elements in row 1, we'll call it energy level 1, and this would be energy level 2, and this gives me energy level 3. And that leads us to our first way of identifying electrons. Our first way to identify electrons is what we refer to as the principal quantum number. The principal quantum number is going to be the energy level of the electron. And so if you're trying to identify the principal quantum number, I can go to the periodic table and find my element, and I can identify where that energy level actually is. Now, there are possible values for my principal quantum number. And by the way, the principal quantum number is commonly abbreviated as n. And if I go back up to Bohr's diagram, you can see n equals 1. Well, that's the first energy level. That's the first principal quantum number. This is my second principal quantum number, and this is my third. That's what that n refers to. Thing about possible values is there's 7. There are 7 rows on the periodic table. The note to make sure that you're aware of, however, is that we have element 118 that has been created in lab, and that fills up our periodic table. If we continue to synthesize elements, and they certainly are trying in labs around the world, then eventually there will be an eighth and possibly a ninth and possibly a 10th row to the periodic table. So for our purposes, when we say 1 through 9, this is going, or 1 through 7, this is only referring to the current periodic table and doesn't include the fact that that may increase to 8 and 9 and 10 when we take a look at it in the future. So, energy levels. Well, when we take a look at energy levels, that gives us one piece. And it's kind of like if I'm giving an address to where you're located. An energy level is pretty generic. If you told me what state you live in, it gives me a general ballpark idea of where you're at, but it doesn't really tell me exactly where you are at because states are pretty big and it would still be pretty hard to find you. So if we're talking about an address and we're talking about an energy level, the generic fact that you might live in, oh, let's say Minnesota, is going to narrow it down if we're talking about the whole United States, but doesn't really give a ton of specifics. We probably need some more information. So when we take a look at Bohr's model has limitations. Bohr's model only works properly with one element, and that's hydrogen. If you look at the drawing of Bohr's model, we're going to see where the problem comes into. Because if in Bohr's model I have these electrons going on this cute little planetary path, what happens to this electron because it's negative when it meets up with this electron when it's negative? And the limitation with Bohr's model is that electrons are negative, and that means they repel. And if you're taking a look at this repulsion, it's like walking through a classroom. Assume all of your classmates are negative. And when we take a look at you walking through a classroom and you're negative and they're negative, anytime you come near one of your other classmates, you're both going to push each other away. And so electrons don't travel in predictable paths because negative charges are going to repel each other. Electrons can't travel in a predictable path. And so putting the path on them is the limitation that doesn't work for Bohr. Instead, what we have since discovered is instead of a pathway, we assign an orbital. An orbital is a vocabulary word you're probably going to want to know. It is just a three-dimensional space where an electron is most likely found. So it's a bubble. I am not going to predict exactly where you are sitting right now. But if I know what room you're in, I have an idea, a ballpark idea of where you're at. So instead of trying to assign exactly your specific spot, we just say you are in a sphere. So during the school day, if I know that during first hour you are in room 452, that means that I can find about where you're at, but I don't necessarily know exactly where you're at. So instead of giving paths, we have areas of space around the nucleus that we refer to as an orbital. And that orbital doesn't predict the path, it just gives me a place where electrons are most likely going to be found. Well, around the organization of the nucleus, then, we have four shapes that we commonly use for orbitals. Those shapes that we use for orbitals are defined as the letters S, which is a sphere. We have P, which has two lobes connected by a node. We have D, and D kind of looks like two P's put together. It is going to be four lobes connected by a lobe. And then we have F, And F has 7 lobes that are all connected together in some way. Now, an atom is three-dimensional. And because an atom is three-dimensional, you will see that these nodes can sometimes rotate. So this would be P aligned around the x-axis. But P could also lie along the y-axis, so we could also call it P as y. And then P could also, in a three-dimensional plane, lie along the z-axis, so you will see P as z. And for D and F, the shapes kind of rotate a little bit and look a little bit different depending on the orientation. And it gets much more complex when you have multiple lobes like D and F. For our purposes, know that they can reorientate themselves in a three-dimensional manner, but we really won't talk a ton about PX, PY, and PZ, although you may see these on a worksheet, you might run into these. These orbitals also orientate themselves to the periodic table. These orbitals are what we refer to as the angular momentum quantum number. This becomes a second piece to the address for an electron. So we've already talked about the fact that n is the principal quantum number. And now we are going to add in a second piece of information, which is the angular momentum quantum number. If we're talking about an address to find you, it would give a city inside of a state. So if I know a state, I've got a general idea. If I have a city, that's going to narrow it down a lot to be able to find out where you are. It doesn't tell me exactly where you're at exactly, but I'm going to be in a much closer position to be able to find out what it is. So the angular momentum quantum number refers to the orbital shape. And we have 4 different orbital shapes. We have S, P, D, and F. And those symbols are going to be, as a quantum number, going to be given the symbol L. So the principal quantum number is N, and the angular momentum quantum number is going to be L. Again, possible values. Well, these are quantum numbers, and because they're quantum numbers, we sometimes give a number value to them. So S is going to be represented by a 0, P is going to be represented by a 1, D is going to be represented by a 2, and F is going to be represented by a 3. So if I'm talking about possible values for this quantum number, it would be 0 through 3. But know that just like with the principal quantum number, the periodic table isn't done. And you might run into F, G, H, or I orbitals that would also be assigned numbers. For our purposes, what we are going to focus on is the current periodic table, not what might exist in the future. So our possible values are going to be 0 through 3 that represent the S, P, D, and F orbitals. These orbitals are orientated on the periodic table as well. Now, what we need to do with this periodic table is we need to get rid of helium over here for the purposes of electrons, and we're going to move helium over here. And if we move helium over here, I can take my periodic table and I can color these and these are going to represent my s orbitals. And for my periodic table, I can take this area over here and this section of the periodic table is going to be represent my p orbitals. The center part of the periodic table is going to represent my d orbitals. And then the last remaining section that sneaks down below is going to be these two rows. And we'll talk more about those in the next video. And these two rows are going to represent my f orbitals. So when we take a look at an address for an electron now, the 2 is going to be my principal quantum number or my energy level. And n is going to be equal to 2 tells me that it belongs somewhere in this second row. And the fact that p is going to be 3 means I can go to 3 and I can go to p. And so n is going to be 3. And 5, well, 5 is going to be my principal quantum number, so n is going to be 5. Now I can take these shapes and I can put my second quantum number by taking a look at up here and know that if it's s, it's going to be 0. If it is p, it is going to be 1. And if it is n, sorry, wrong thing. If it is d, it is going to be a 2. Now, one thing we need to quick take a look at is energy levels for the other orbitals, because energy levels for the other orbitals do have a little bit of a change. So for this periodic table for electrons, we move helium over and get it from here. But I know now that these are going to be my s orbitals. And for my s orbitals, I just need to number the rows 1 through 7, and that gives me my s energy levels. But I know this section right here is going to be my d orbitals, and let's do p first. My p orbitals are going to be here. And what do I know about my p orbitals? Well, their energy levels are going to be the same as my s, but there's something missing. So there's not going to be a 1p because there's not a row here. And that means if I'm numbering my p orbitals, this is going to be a 2, 3, s is 4, so p is going to be 4, s is 5, p is going to be 5, and so on in 6 and 7. Now, d energy levels. D is a bigger orbital. And because D is a bigger orbital and it's out further from the nucleus, its energy level gets changed a little bit. And so when I take a look at my d orbitals are going to be whatever my s is minus 1. So that when I am looking at my d orbitals here, my s is going to be 4, and 4 minus 1 gives me 3d. 5 minus 1 is going to give me 4d. 6 minus 1 is going to give me 5d. And 7 minus 1 is going to give me 6d. And last but not least, we have our f orbitals. And f orbitals are going to be the same as my s minus 2. But wait, where do these belong? Well, if you look at your periodic table, not all periodic tables agree because not all chemists agree. But in general, this is going to be element 55. This is going to be element 56. And where does the disagreement go? Well, is this 57 and this 58? Or is this 57 and this 58? Different periodic tables have different arrangements. And you'll have to look at the periodic table that you're expected to use, but this block goes somewhere right in here. And depending on which version of the periodic table, it might include these two rows, or those two rows might be put down here, which pushes the rest down. So what do I know? Well, my F will fit in my 6 energy level, but 6 minus 2 is going to leave me with a 4F And this one is 7 minus 2, which leaves me with a 5f. Now, at this point, this might seem like a bunch of gibberish. But when we take a look at your quantum numbers and take a look at electron configurations, generally understanding is not found in one day because it's incomplete. Tomorrow, we're going to put these pieces together and take a look at the electron configurations and how these work for the electron configurations. So if this doesn't make complete sense, hang in there and we'll help you out in part 2 of the video. So you guys have yourselves a great day.